let's just give an introduction to the next big thing, which is vector calculus. Let's talk about what we're going to want to calculate and what we're going to have to do to get there. The background that we're going to need in building vector calculus is we're going to have vector valued functions. So the first thing that we need to deal with is vector valued functions. What we have here with vector fields or vector valued functions is exactly what it says on the tin. A function that assigns a vector to every point. So here our function assigns a vector to each point rather than a scalar. So the output at each point is a vector instead of a scalar. So we take a vector field of a point and we get a vector. So we have a function that is assigning to each point a vector instead of a scalar. So instead of saying the temperature at 0, 0, 0 is 65 degrees, we say the velocity at 0, 0, 0 is this vector. We assign a vector. So the vector valued function assigns a vector to each point. That's the difference. Input point, output vector. Another thing that we're going to have to deal with is we're going to want to describe a one-dimensional curve in three-dimensional space. So we're going to need to parameterize curves. Specifically, we're going to be doing this in R3. We don't spend a lot of time parameterizing curves in R2. Because they're one-dimensional curves in two-dimensional space. Most of the time, we get away with functions, we get away with equations. We don't gain as much out of parameterizing curves in R2. But in R3, suddenly it becomes necessary. We need to be able to describe one-dimensional curves in three-dimensional space. We want to describe a one-dimensional curve in three-dimensional space. We know that if we make an equation of three variables, that will give us a surface. If we make a function of two variables, that will give us a surface. So functions and in two variables or equations in three variables produce surfaces. But integration is a game of plug this stuff into and calculate it. Plug this stuff into this expression and then add up the results. Plugging in a bunch of stuff in three-dimensional space, that collection of stuff that we plug in might be a one-dimensional curve rather than always a surface or a surface. So remember that a function of two variables or an equation in three variables describes a two-dimensional surface. We need to be able to describe a one-dimensional curve in three-dimensional space. So the new thing that we're doing here is describing a one-dimensional curve in three-dimensional space, rather than a two-dimensional surface or two-dimensional surface in R3 described by a function or an equation. So what is the, where does the vector calculus part come in? So this is just vector fields and curves in R3. Where does the vector part come in? The vector part comes in as far as the multiplication that we're going to be using. In vector calculus, the multiplication gets upgraded from our scalar multiplication to vector multiplication. And we got two kinds of vector multiplication. Our favorite, the dot product, and the cross product, since we are going to be in R3. So the other thing, the calculus part, the integration will be vector multiplication. The integration that we'll be using, that we'll be calculating, will be based on vector multiplication. Integration is multiplication, but one of the factors is continuously variable. In vector calculus, that multiplication is going to be described with a dot product or a cross product, mostly a dot product. Integration is multiplication, but one of the factors is continuously variable. Integration is multiplication, but one of the factors is continuously variable. The multiplication that we've been doing so far has been just regular scalar multiplication. Now we're going to be doing vector multiplication. That's the change that we're going through dealing with vector calculus. This is a gross oversimplification of vector calculus. But it does fit into the description of the same stuff that we've always done with fancier inputs. Any questions? Comments? Snide remarks? Too much for a Monday? Because this is the Monday before spring break. No one will have it. I can get away with a lot this week. I could go directly to the fundamental theorem of calculus with vector calculus, and everybody's like, oh, no questions. I will worry about this during spring break. Which means I will not worry about this during spring break. I think so. Let's talk about why this is necessary. Let's remind ourselves what integration looks like. So the integration, when we write an integral, So let's say we have like a simple integral, an integral over a definite integral. This is the integral from a to b of f of x to x, where I is just the interval from a to b. I'm just rewriting this to make it look like the integrals that the way we write double integrals and triple integrals. What this expression is asking you to do is evaluate f of x dx at all the values of x listed in the integral part, listed in that interval. So the instructions here are to evaluate f of x to x at all the points in I, then add the result. This we recognize as being very suspicious because we want to add a bunch of stuff up that comes from a continuum. We're taking a continuum and we're adding it up, but this is what integration is about. Integration is continuous addition. You can also think of it as accumulation. This is just how this set of symbols works. So even if I say the integral over r of f of xy dA. In this case, r is just a collection of points xy that we're going to be evaluating f of xy dA. So r is some region which just means it's a bunch of xy. It's just a bunch of points xy. And what do we do with this double integral? We evaluate f at xy dA at all the points xy evaluate f at xy dA at all the points xy in the region R. It's just a bunch of points. Then add the results. I forgot I didn't want to cram these up together. In triple integral. Oh, and we did this in rectangular coordinates and polar coordinates. So instead of f of xy, we might have f of r and theta times r dr d theta. When we have the integral over some solid w of a function of 3 variables, we evaluate the expression f of xyz dv at all the points xyz in the solid w. Then add the results, because w is just some solid. It's just a bunch of points x, y, and z. So once we evaluate f at x, y, z, dv, we add the results. This is all the types of integration that we've dealt with so far. And we applied the same fundamental theorem to all these types of integration. Add one of the exponents, divide by the new exponent. We even learned how to escape things like trigonometric substitution by using better coordinates. Make the change up what we do here, where we evaluate, and use a function that's easier to deal with, that describes round things better. In each of these three cases, the operation that we're dealing with is we're doing multiplication. Really, we want to think of this as continuous addition. But that's just what multiplication is. Multiplication is addition when everything is the same. When everything isn't the same, we just got to use addition. When everything isn't the same over a continuum, we have to use integration. That's the hierarchy. You learn addition, you learn the shortcut multiplication. You learn when you can use that shortcut of multiplication. And then in calculus, we just make the variable continuously variable. But we just had scalar, regular multiplication. All we're doing in vector calculus is trading our regular multiplication for vector multiplication. Vector integrals we're trading our our irregular multiplication for a dot product. So what we got going on here is C is some one-dimensional curve in R3. That's just a bunch of points x, y, z in R3. But rather than being a solid, all coming from a solid, we could describe with some solid that we can describe x with x, y, and z. It's just a one-dimensional curve in R3 or a path in R3. dr is the same as dx, dA, or dv. dv, if you recall, would have been like some small chunk of w. Just like dA was some small rectangle in the area, in the region. Just like dx is some small bit of the interval. In the same way, this dr is going to be some small bit of the curve C or the path C. Our interpretation has changed because our multiplication is now a dot product rather than just a scalar product. I knew I was going to be doing this. I should just like use the generic star for our regular multiplication. Our multiplication is now a dot product. So we're asking a slightly different question. We've got dot product as our multiplication now. So what is this calculation? I've got the vector field assigning at every single point some vector. And I'm seeing what happens as the curve goes through that vector. dr would be like the direction of the curve at that point. And I'm finding the dot product. It's multiplication at an angle. I'm taking the vector from the vector field and multiplying it by the direction of the curve, but multiplying at an angle because we have a dot product. Once we multiply at that angle, once we calculate this at all the different points, as the vector field changes and as the curve travels through the space, we evaluate f at x, y, z dot dr. At all the points. On the curve, then add the results. We're not doing something new. It's still just integration. It's still just accumulation. Continuous addition. Multiplication, but one of the factors is continuously variable. We need to understand what this vector field is, capital F at x, y, z. We need to understand how to parameterize a one-dimensional curve in three-dimensional space so that we can perform this multiplication, so that we can add up all these dot products and then figure out what this represents. So when we start thinking about applications of vector calculus, we want to think about what are the applications of the dot product. When do we want to multiply at an angle? Usually at this point in your mathematical career, dot product shows up most when you're working with a function that represents a force. This is like our go-to thing for vectors, some kind of force. So, going back to my previous example, at this point, actually I decided to move the origin up to my shoulder height so I could point to things and it could be like the row. But here's the origin. A scalar function of 0, 0, 0 might say that is the temperature at this point. So just 70 degrees or 68 degrees, whatever it is. And then that temperature changes as we move around the room. But the force at 0, 0, 0 might be the vector. Let's see, I'm gonna push my finger in. -1, -1, 0. The force is me pushing on this point. So there's a vector at that point. Or if we think about like the airflow in the room, kind of weird going into this corner, but there's some airflow in this corner. And then so the air comes in, and then maybe it's like going directly up because it goes into the corner, like shoots straight up and then starts curling around. At every point, there's some vector demonstrated, giving the direction that the air is flowing at any point. Now, instead of a scalar at every point, we have a vector at every point. We're going to do the same thing. We're going to grab a bunch of points in this space, and we're going to find a dot product using two vectors. One from the vector field and one from the path or from the surface. Then we just dot product, add them up. Hopefully, some fundamental theorem shows up and explains how we can calculate this without having to add up an uncountable infinity of products. Okay. In this case, I talked about the curve. So there's some curve rolling around in R3. It's gonna have to have a direction. The dr would just be a little piece of tangent vector at any given point. This curve is just we're gonna think of this curve as just a bunch of tangent vectors. In the same way we thought of an interval as a bunch of dx's, or sorry, delta x's. When I'm integrating over a curve, this is going to be a tangent vector. When I'm integrating over a surface, what's one vector that I'm going to stick at every point on the surface? Can I use a tangent vector there? Surface, point. Can I use a tangent vector? Why can't I use a tangent vector? How many tangent vectors we got at this one point? No. Infinitely many, because there's a whole plane tangent to the surface. But in R3, what's one vector I can get at that point related to the tangent? The normal vector. At each point on a surface, there's a bunch of tangent planes, so they can't get one vector out of that. But if I grab the normal vector, there's always just one normal vector. So when this jumps up to being some surface in R3, instead of dot dr, I'm just going to dot dn, some normal vector. See, you already have calculus instincts. It's the stuff that you just, the way you just think about it. All right, I have some problems for you. These go back a couple of weeks. This is a piece of paper with some problems on it, and you are going to be turning this paper in. You can help each other on this because that's the only thing that humans really should be doing, helping each other.
Oh, crap, this is half physics already.
So the problem is about charge density. I vary the charge density going from left to right. So that, but at every point, at a given point X, it's the same charge all the way up and down. Before you even begin, or maybe at the end, do a reality check. Which of these plates, based on what the density looks like, which of these plates will have a higher charge density? Because if it doesn't work out that way in your calculations, then something went wrong in your calculations. So always do a reality check at the end. As usual, you could work with each other. We're not going to break into formal groups because that takes too much. So here's one problem. Let's just find the charge density of each of these plates.